From this slide, we will discussing about introduction, contents, for example question, conclusion, and references. Let's begin with introduction. What is logical equivalence? Logical equivalence is when propositions P and Q are logically equivalent if P by conditional Q is a tautology. The equivalence of two propositions can be established by constructing a truth table. Two propositions are said to be logically equivalent if their truth tables are identical. While constructing a truth table, some propositions may contain all truth values of their variable as true only, which is tautology, or false only, which is contradiction, or both true and false, we call as contingency.
Okay, let's talk about statements that are not logically equivalent. The statements are not logically equivalent if their true values are not always the same in all cases. This means there is at least one case where one statement is true and the other is false. In other words, the statements are only logically equivalent if they always share the same truth table, whether both are true or both are false. For example, think of statement like if it rains, the ground is wet, and if the ground is wet, it rains. They might seem similar, but are not logically equivalent. We will start this with a truth table in the next slide.
In mathematical logic, a conditional statement is written in the form P implies Q, where P represents the hypothesis and Q represents the conclusion. The statement means that if the hypothesis P is true, then the conclusion Q must be also true. From this conditional statement, three related statements can be formed: the converse, the inverse, and the contrapositive. The converse is obtained by switching the hypothesis and the conclusion, resulting in the statement Q implies P. The inverse is obtained by negating both the hypothesis and the conclusion, giving not P implies not Q. The contrapositive is formed by switching P and Q and negating both, which result in the statement not Q implies not P. It is important to note that the contrapositive is logically equivalent to the original conditional statement, where the converse and inverse are not logically equivalent to the original statement, but are logically equivalent to each other.
Example 1. Construct a truth table to determine whether P implies Q is logically equivalent to not Q implies not P. First, we have to do a table that consists of 7 columns and 4 rows. Number of rows is determined by formula 2 to the power of n, where n is the number of variables. In this question, we have two variables which is P and Q, so 2 to the power of 2 equals to 4. Name each column as P, Q, not P, not Q, P implies Q, and not Q implies not P. Then insert the truth value for P and Q first. For P, first and second row is 0, while third and fourth row is 1. For Q, first and third row is 0, while second and fourth row is 1. Then put the truth value for not P and not Q. Truth value for not P and not Q must be vice versa from P and Q. Then we have to find the truth value for P implies Q. If both P and Q is 0, or P is 0, Q is 1, or both P and Q is 1, the implication is 1. However, if P is 1 and Q is 0, then the truth value is 0. Name column P implies Q as A. We do the same thing for not Q implies not P and name the column as B. The last column will be labeled as A, logically equivalent to B. By referring to column A and B, find the truth value for the last column. Therefore, we get the truth value for all rows is 1, which is true. Hence, we can conclude that the truth table shows P implies Q is logically equivalent to not Q implies not P because the last column shows tautology.
Example 2. construct truth table to determine whether the negation of P and the negation of Q, or the negation of P and Q, or P and Q is logically equivalent to P implies Q or not. So, 1 denotes as true statement and 0 denotes as false statement. The P for this question is 0011 and Q 0101. Not P, we will get 1100. And not Q, we will get 1010. As we know, if P is true and Q is true, then P and Q is true. Otherwise, P and Q is false. For the disjunction, if P is true or Q is true, or both P and Q are true, then P or Q is true. Otherwise, P or Q is false. For the conditional statements, if P is true and Q is false, then the conditional P implies Q is false. Otherwise, P implies Q is true. If P and Q have the same truth value, then P if then only Q is true. And if the opposite, it is false. Not P and not Q. We will get 1000. This column will be BA. For the column B, it is not P and Q. We will get 0100. For the C column, we will get P and Q, which is 0001. And for the D column, it is A or B. We will get 1100. For the column E, we will use the D or C, which is we will get 1101. Lastly, for the column F, P implies Q. We will get 1101. From the column E and F, we can see that the propositions are identical. Therefore, the propositions are logically equivalent. For E, if and only if F is 1111. It shows that this is tautology. It is because tautology is a statement that is always true regardless of the circumstances in mathematics.
Okay, now let's look at the truth table for P equivalent Q and Q equivalent P. We will apply these two logical expressions to determine whether they are logically equivalent. Here, we have all the possible combinations of truth table. For P, it's ring, and Q, the crown is sweet. Let's walk through each round to determine the truth value. In the first round, when P and Q are both false, P equivalent Q and Q equivalent P are true, the biconditional is true. In the second round, P is false, but Q is true. Here, P equivalent Q is true, but Q equivalent P is false, so the biconditional is false. In the third row, P is true, but Q is false. P equivalent Q is false and Q equivalent P is true. Therefore, the biconditional is false. In the fourth row, when both P and Q are true, both P equivalent Q and Q equivalent P are true, and the biconditional is true. If we look at the last column, we will see that the biconditional is not always true. It is false in row 2 and 3, which tell us that P equivalent Q is not logically equivalent to Q equivalent P. So, the true expressions are not logically equivalent because their truth value different in some cases. This is how truth table help us to determine whether the logical expressions are equivalent or not.
Next, we continue with example. Write the converse, inverse, and contrapositive of the following statement using symbolic logic and words. The statement is, if the shape is a triangle, then it has three sides. So, P, the shape is a triangle, and Q, it has three sides. The converse is Q implies P. So, if the shape has three sides, then it is a triangle. The inverse is not P implies not Q. So, if the shape is not a triangle, then it does not have three sides. The contrapositive is not Q implies not P. So, if the shape does not have three sides, then it is not a triangle.
To conclude, in logical equivalence, we will be able to construct the truth table and determine the logical equivalence. We can differentiate between conditional, inverse, converse, and contrapositive. In logical equivalence can be applied in many different situations in our daily life.